In this last video, we're going to talk about the formation of smog, and there are two basic kinds of smog with very different chemistries. One is sort of the classical smog, and which doesn't happen quite as much anymore, and the photochemical smog. So classical smog is sort of the kind of smog that we think about when we think about the London smog, in particular that event in 1952 in which a lot of people died. So the London type smog occurs in areas with high emissions of sulfur-containing compounds. This is usually through burning of coal that contains sulfur impurities. And the air also has to have a relatively high water content, for example, with fog. So in this case, we get burning of sulfur-containing coal, and then we have which releases sulfur dioxide, so that's that SO2, and soot, so some hydrocarbons there as well. So if we add an inversion, which means that sulfur dioxide and soot is going nowhere, and add in also fog or water droplets, what we end up with is sulfuric acid in fog droplets. So you can imagine this going bad rather quickly. So here's the reaction, which you've probably seen before when thinking about acid rain. So we've got sulfur dioxide plus water, so it goes into the fog droplets and forms sulfuric acid, and you get an acid fog, just like with acid rain. Except that people tend to breathe the acid fog, which is where the main problems come from. So you have these acidic particles or water droplets, high smoke density, and both of these things combined really inhibit lung function and can cause death. So this is what happened in London, and it's also what happened in Donora, Pennsylvania, I think in the late 40s. So this is much less common now in the US since the Clean Air Act, and we take a lot more measures to avoid putting sulfur dioxide into the atmosphere. So photochemical type smog is sort of what we think about when we think about LA type smog. So this is a little tougher to control, the chemistry is a little bit more complicated, and it definitely still goes on. So here, what starts the whole cycle is the emission of nitrogen oxide from tailpipes. And again, this is nitrogen and oxygen in the air combined with really hot engines sort of creating this environment where nitrogen oxide is coming out of tailpipes. So over time, oxygen actually combines with nitrogen oxide to form nitrogen dioxide. So this is sort of slow, not terribly slow, but it happens sort of through the course of the morning. So first thing, you have rush hour, people going out driving their cars, producing a lot of NO, and then over sort of the course of the morning, you get the NO sort of getting transformed into nitrogen dioxide, or NO2. And this then begins this whole ozone NOx cycle. So the NOx just stands for these different nitrogen oxides, so nitrogen oxide and nitrogen dioxide. So I put this figure up here. It's from the book that used to be used for this class, just in case there's somebody that thinks well in this way. And when I look at this diagram, I just sort of get confused, but maybe these arrows and things work for you. Essentially, these equations here, this is equation 1, so this is once you have this nitrogen dioxide, it interacts with light, reforming nitrogen oxide plus an oxygen radical here. And this oxygen radical interacts with regular oxygen in the atmosphere to form ozone. Ozone plus the NO formed up here reforms nitrogen dioxide and oxygen. So that is why we call this a cycle. So you start with the nitrogen dioxide and come back to the nitrogen oxide in the middle, sort of forming this reactive oxygen and oxygen gas, which forms ozone and interacts with this whole cycle here. And these are some other alternative pathways for nitric oxide or nitrogen oxide, whichever you prefer, that we'll talk about in a little bit. But first we're just going to focus on this sort of group of reactions. So this is my little animation of this process. I also posted another animation that you can look at if you prefer that one. But so here is our nitrogen dioxide. Sunlight comes in and breaks this bond. creating nitric oxide or nitrogen oxide and a reactive oxygen molecule or atom that combines with regular oxygen gas to form ozone. And then this ozone plus a nitrogen oxide reforms nitrogen dioxide and a normal oxygen molecule. So you start off again where you started. And this sort of cycle could just continue. So this is what it looks like through the day. So you start off with rush hour, which creates a lot of NO. That gets slowly transformed to NO2. And then you start getting bright light, intense sunlight here, which starts cleaving these bonds. And that's when you get the formation of ozone, sort of later in the day. And then as the day goes on, you get this cycle kind of returning and forming, getting rid of the ozone. Okay, so ultimately the amount of ozone in the atmosphere should be limited by the amount of nitrogen oxides. But we also have these other things going on. So it's not just these three compounds in the air. Fossil fuel combustion or incomplete fossil fuel combustion also forms these other sort of hydrocarbon fragments and also these reactive radicals. You remember earlier we talked about how ozone can react to form a hydroxyl radical. So there's these other pollutants formed from hydrocarbons that can oxidize NO and NO2 without consuming ozone. So instead of this happening, we've got these other volatile organic compounds reacting to form peroxide radicals that oxidize the NO. So instead we've got this coming in, reacting with the NO to form some other molecule, and so that leaves the ozone in the atmosphere. So you get higher amounts of ozone than you might expect if all that was going on was this cycle. And we've also got ozone reacting with hydrocarbons, so that creates its own sort of visible cloud of smog. So I'm not going to go into the chemistry here. This is pretty complicated chemistry, but just know that this is also going on. So there's sort of all of these reactions going on that result from the NOx in the air and then the ozone and the hydrocarbons all coming together to form this lovely smog that we have here. So we do need the NOx and the hydrocarbon to get a buildup of ozone and nitrogen dioxide. And nitrogen dioxide is actually a brown colored gas, so that's what gives you this brown haze. But it's the ozone plus the hydrocarbons that give us sort of the particulate smog component. So you need all three of these things to really make the really dense photochemical smog that you might see around LA or in parts of China. Okay, and that is it for smog. We'll talk about acid deposition, potentially, and stratospheric ozone. We'll see how far we get, because we're going to do some other things in class on Thursday, or on Tuesday after break as well.